Hi guys, welcome to the next section, Release Management Continuous Delivery. Now, we move on to the first video of this section that deals with the test system. We've spoken several times about the Big Bang event that a deployment is. This is something that I always try to avoid when I set up a new system. Releases should be smooth events that can be done at any time without effort, and you should be able to roll back within minutes with little to no effort. This might be a gigantic task, but once you provide a solid foundation to your engineers, marvelous things happen. They start being more efficient. Let's talk about statistics. When we are creating a deployment plan, we're creating a system configured in series. It is a finite list of steps that will result in our system being updated. First step is copy a jar file into a server. Then stop the old Spring Boot app. Next step is copy the properties files. And finally, start the new Spring Boot app. If any of these steps fail, the whole system fails. This is what we call a series system. The failure of any of the components compromises the full system. Let's assume that every step has a 1% failure ratio. 1% seems quite an acceptable number until we connect them in a series. Let's assume that we have a deployment with 10 steps. These steps have a 1% of failure rate, which equals to 99% of success rate, or 0.99 reliability. Connecting them in a series means that the whole reliability of our system can be expressed like this. This means that our system has a 90.43% success rate, or in other words, 9.57% failure rate. Things have changed dramatically. Nearly 1 in every 10 deployments is going to fail. Nearly 10% is quite a lot for depending on the systems. It might be a risk that we're not willing to take, so why don't we work to reduce this risk to an acceptable level? Why don't we shift the risk to a step that does not compromise production, and we reduce our deployment to a simple switch that we can disconnect at any time? These are two concepts called canary and blue-green deployments. Let's see the test system. In order to articulate a continuous delivery pipeline, we need a system to play with. The system is very simple. Let us look at this diagram. As you can see, we have 3 services. The first service is an API aggregator. Next service translates a timestamp into a date in ISO format. And the last service that translates a timestamp into a date in UTC format. These services work in coordination to translate a timestamp into a date in different formats. But it is also open to extensions, as we can aggregate more services to add more capabilities and expose them through the API aggregator. Every service will be packed into a different Docker image, deployed as a deployment in Kubernetes, and exposed via services to the cluster and to the outer world in the case of the API aggregator. Let's see ISO date and UTC date services. The ISO date service simply takes a timestamp and returns the equivalent date using the ISO format. Let's take a look at its code. The service itself is very simple. It uses a library called Moment and a framework called Happy to provide the ISO date equivalent to a timestamp passed as a URL parameter. The language used to write the service is Node.js, but you don't need to be an expert in the language. You should just be able to read JavaScript. As with every Node.js application, it comes with a package.json that is used to describe the project and its dependencies. Here is our package.json file. Some fields of the package.json are customized, but the important parts are the dependencies and the scripts sections. Now, one important file is left, that is the Docker file. In order to test our service, let's build the Docker image. Let's run docker build command. After a few seconds, our image is ready to use. We just run it. And that's it. In order to test it, we use the curl command to get some results. This will return a JSON with the ISO date representation of the timestamp passed as a URL parameter, as you can see in the terminal. The UTC date service is very much the same, but with different code and a different interface. As you can see, there are some changes, like the port is 3001. The date returned is the UTC date, which is basically the ISO date without time zone information. We also have a Docker file, which is the same as for the isodate service, and a package.json file. There are minor changes. In total, you should have these files in the UTC date service. Docker file index.js with the code from package.json. If you want to make your life easier, just clone the repository at this link so that you have all the code ready to be executed. Now, in order to test that everything is correct, we build the Docker image, and then run it. Once it is started, we should have our service listening on port 3001. You can just check by executing the curl command. This in a manner similar to isodate service. It should return a JSON with the date, but in a UTC format in this case. Now we will see Aggregator Service. The Aggregator Service is the microservice that aggregates the other two services. It also provides a front API for consumers so that all the logic behind the scenes gets encapsulated. Even though it is not perfect, this is a common pattern because it allows us to play with the idea of circuit breaking as well as manage the errors on a dedicated layer. In our case, the service is quite simple. First, let's take a look at the code. In order to simplify the understanding of the code, we did not use promises or async, or await in it at the cost of having a nested callback. Here are a few points to note. We are calling the services by name, leveraging the communication to the Kubernetes DNS. Before returning, Aggregator Service issues a call to the two services and returns a JSON object with the aggregated information. In order to test this service, we would need to create DNS entries pointing to isodate service and UTC date service. It is harder than testing it in Kubernetes, so we'll skip the testing for now. As with any node application, the aggregator service needs a package.json to install the dependencies and control a few aspects. The package.json is very important. The scripts block particularly instructs us on what to do when the npm start command is executed by the Docker container based on the image defined in the Docker file. By now, we should have 3 files: index.js, Docker file, and package.json. Now, we will build the Docker container with the docker build -t aggregator command. Let's check whether it works as expected. Even though the server won't be able to resolve requests because it does not know how to communicate with isodate service and UTC date service, it should start. Let us see pushing the images to Google Container Registry. So as of now, we have 3 images in our local repository: isodate service, UTC date service, and aggregator. These 3 images live in your computer, but unfortunately our Kubernetes cluster in the GKE won't be able to reach them. The solution for this problem is to push these images into a Docker registry that will be reachable by our cluster. Google Cloud provides us with a Docker registry, which is extremely convenient for using with GKE due to several reasons. The first reason is data containment. The data never leaves the Google network. Next reason is integration. Services in GCP can interact with implicit authentication. Next one is automation. This integrates with GitHub and other services so that we can build our images automatically, creating a pipeline of continuous delivery of images. Before setting up a continuous delivery pipeline with Git, we're going to push the images manually in order to understand how it works. Google Container Registry is replicated across the globe, so the first thing you need to do is choose where you want to store your images. In my case, eu.gcr.io is the perfect match. Then we need our project ID. This can be found by clicking on the project name in the top bar of the console. In my case, the project ID is Deploy Software on Kubernetes. Now, the third component is the name of the image that we already have. With these 3 components, we can build the name for our Docker images URL. Now, it is time to tag our images as appropriate. First up is the isodate service. Then there's the UTC date service. And finally, we have the aggregator service. This is the mechanism that Docker uses to identify where to push the images. Docker reads the name of our image and identifies the URL to which the image is to be pushed. In this case, as we are using a private registry, we need to use credentials, but using the gcloud command, it becomes quite easy. Now, it's time for the ISO date service. And finally, there's UTC date service. Be careful. The project ID will change, so customize the command to fit your configuration. After a bit of time, the images are up in our private instance of the Google Container Registry.